Good morning, good afternoon, and good evening, wherever you are. We welcome you back to another CIQ Roundtable. So we had one of these week before last, and it went over really well. So we invited a group back to continue that conversation and kind of see what else we can get from people who are in the industry and actually have real world use cases and talking points. So if we could go ahead and bring in the panel. Well, there's Greg. Well, welcome back, everyone. We've added some new ones this week too. We're missing one. Is Forrest going to join? If not, we'll go ahead and get started. So I think last week, everybody got to meet Patrick and John and Gary and Greg as always. So I think we'll start with the new guy in the room. If you would go ahead and introduce yourself, Krishna, and let us know who you are, where you're from.
Hello, I'm Krishna Muriki. Right now I am employed with Cable Corporation, but I go a long way with Greg Kudzer and Gary Jung, both of them here on the panel. Before this, I was employed at Lawrence Berkeley Lab at UC Berkeley. Greg hired me into that position at Berkeley, and Gary was my manager and guide and mentor. So yeah, I know the panel very closely. I have worked with Patrick. I have exchanged on Slack. I learned a lot from Patrick. I know him. Glenn, good friend of mine. Yeah, glad to be here. So I'm about 10 months old at KLA Corporation right now. So we, in this organization, we make wafer inspection devices. So in semiconductor industry, it's very crazy right now with all the chip shortages. The demand for our products is really high, and it's a little bit crazy. And we are having to stretch ourselves in terms of our HPC designs and HPC technologies. We are adopting to meet this growing crazy demand. Yeah, this topic is really interesting. I'm glad to be here.
Very nice and welcome. So I'm going to go around the screen real quick. Just introduce yourselves very quickly again. I think because you've introduced yourself last night, you don't have to go into a lot of detail, but I'll start with you, Patrick, because you're at the top of my screen here.
Howdy. Well, my name's Patrick Roberts. I currently work with Skyworks. Skyworks, we design all sorts of different types of chips for all sorts of different things. So sorry, that's rather vague, but we're in all sorts of RF chips, analog chips, digital chips, big and small. So been around for quite a while. They used to be Rockwell long ago. So some of you may be familiar with that. It depends on your age, I suppose. But I've been in HPC specifically for a little over 20 years. I've been in the IT industry for 29 or so years. So that's about it.
It goes fast, doesn't it, Patrick?
It does indeed.
So next we have John, aka Grisnon.
Hi, John Hanks. Been doing this for a long time. I don't remember what I said last time when I got introduced, so I hope I don't contradict myself this time. I was thinking about the topic today, and I think maybe I'm inherently unqualified to answer this question or even try to answer this question because in pondering it, I think all I do is manage workstations now. They just happen to look a lot like a cluster because of the way I manage them. So I don't know that I even do any HPC anymore.
No, I think that's great. And that's something that's going to be interesting to kind of see. I mean, what is HPC to everyone else? So I'll move next, kind of skip over Christian because we had you. Greg, you're in the middle.
Hi, everybody. I feel like who is in the Brady Bunch in the middle? Was that Alice?
Jan. No, I'm kidding.
Jan, thanks. Hi, everybody. I've been doing HPC pretty much my whole career. Started with a degree in biochemistry and then failed to continue getting my PhD because I got more interested in computing and Linux and open source than doing the science. So I've been really focused on HPC and scientific computing ever since. And as Krishna mentioned, I've worked with Krishna and Gary for ages and at Berkeley Lab. So it's great to have this middle line across the board is the Berkeley crew here, I think.
Very nice. We'll just call it the Berkeley line there. So next person from Berkeley, Gary. Gary. Wow.
Hi, my name is Gary Zhang. I manage the institutional HPC computing at Berkeley Lab. Greg and I started the program back in 2003, and it's been going great since. I also have a dual appointment with UC Berkeley, so I manage the HPC effort for the institution down at UC Berkeley also. And Krishna and Greg and I, we go way back doing this.
Very nice. Glenn, you're up next.
Can you guys hear me now?
We got you.
Yay! Glenn,
and you gotta show us your shirt today too. By the way.
Been at CIQ for 16 days. I'm the VP of frickin' Sweet Ideas at CIQ, and my background was a doctorate in immunology, microbiology, postdoc in HIV research, and then left academia and fell into HPC with my second postdoc at the San Diego Supercomputer Center. And from then on, I was like in '99. From then on, it's been, bioinformatics and HPC has been my livelihood. So incredible. And since about 2000, I've known Greg, I think. So I blame him.
It's an easy target, right?
Yeah.
Forrest.
He's in the middle.
Exactly.
Hey, everyone. My name is Forrest Burt. I'm a high-performance computing systems engineer here at CIQ. I've been with CIQ for about a year. Before that, I was the student HPC system administrator at Boise State University while I was getting my bachelor's in computer science. I kind of got my start in the cloud and in computing and stuff like that, in the early 2010s, messing around with, the tech that I had available and, cloud gaming servers and stuff like that. I'm real pleased these days to work with a little bit bigger systems. But yeah, I love HPC, got super interested in it while I was in college. And I'm really pleased to have been working at CIQ and to be working on everything that we do with Fuzzball and that type of stuff. So great to be here.
Thank you, Forrest. So kind of jumping back into the question of kind of what John started to allude to a little bit. And I think that the definition of HPC is going to be a little bit different to everyone here. So kind of like to go around and ask, what does HPC really mean to each of you? And just kind of tell us what that means. Tell us a little bit about maybe where you got to that point and how you got there. And start off with Patrick.
And keep picking on me.
I know, you're right next to me.
I would say, what does HPC mean to me? So HPC to me is any service which is designed specifically to perform a set of complex tasks, which I know that is a very broad definition, but it's very true because I've dealt with HPC in all of its various forms, from craze to working on loose grid systems to working on close coupled, very tight systems with Infiniband and Miranet and just all sorts of different interconnects of all kinds. And it really just depends on what tasks you're trying to accomplish, what you need in order to meet that task out. It kind of, there's a blending of there's HPC for high performance computing, and then there's now high throughput computing, and now there's like all these other subvariants. But in my mind, it's all HPC. It's just with different tasks in mind to accomplish, and different hardware and software solutions to accomplish those tasks. So for me, it's just kind of one really big bucket of designing clusters and computers to meet tasks needs. So.
No, that's great. Thank you, Patrick. And John, you kind of started down a road of talking about desktops, and that's kind of what you deal with today. I know that may have been a little bit tongue in cheek, but in reality, that can kind of be something that really is the case. So tell me about your definition of HPC.
For me, HPC, the primary thing there is high performance, and for it to be HPC, it needs to be high performance, and that's why a lot of what I do now is not HPC, because I got people getting, this massive pile of GPU hardware and memory and cores, and then sitting there typing in a Jupyter notebook on that system. It's like as far away from high performance as you could ever hope to get. Somebody checking out a $7,000 GPU to type and hit enter at a command line prompt. So I think it's the HPC, high throughput computing. Those are really the two main designations. And then for me, it's getting even further away from high throughput computing, where, yeah, we run some embarrassingly parallel workloads, but the most important thing in our environment is on demand for people interested. So we're pushing that long tail even further out by pulling in people that don't really need a cluster. They just need a well-managed desktop workstation that has a lot of memory.
Very nice. Thank you very much. Krishna, how do you define HPC?
I think it is changing. Is my audio better now?
You're good.
Okay. I think the definition of HPC is changing. 2005, when I started my first job in US, it was at San Diego Supercomputing Center, and the first machine I worked on was from IBM. It's called DataStar. It has a very specialized interconnect, very specialized servers all put together. But that's not the high-end machine back then. San Diego Supercomputing Center had a good-sized machine, DataStar. That's how the HPC mission used to be, and the applications that used to run on that application was very optimized, tuned for the architecture, that IBM architecture that we use. But these days, I think it's not the case anymore. A lot of technologies have commoditized interconnect. Infiniband is treated as a commodity. A lot of servers that we use on even the top machines, the top 500 machines, are commodity servers from Supermicro and things like that. I think it is morphing. The definition for HPC is becoming a lot more commoditized and not specialized machines anymore. The employer who I work for right now, we build stream computers. All that we have is a lot of data streaming at us, wafer inspections, right? So we have really high definition cameras looking at this nanoscale layer width, transistor width, and things like that. So it's really high volume data, just fire hose of data being shoved at us. The biggest machine that my employer built is just 3 racks, not hundreds of racks or even tens of racks. It's just 3 racks. That's the biggest that we have. So and it's all commodity hardware. Commodity. We don't have a specialized server design team at KLA. We don't have a specialized architecture team at KLA. We all take white boxes, Supermicro, Infiniband commodity, and just try to build. I would consider what we are doing at KLA is HPC, because the data volumes that we are dealing with, if that's the definition, it does come under HPC. But the hardware-wise, it's all off the shelf. So it is changing. HPC definition is surely changing, is what I would say.
No, that's very interesting. I mean, talking about commodity hardware versus very specialized hardware that it used to be. So I think, like you said, things have changed.
I don't think that's inherently a bad thing, though. I really think that commoditization of the hardware has brought HPC into the hands of so many more people that it's actually a very good thing that, you can build a super equivalent with off-the-shelf parts. I mean, I did it for a very, very small, but one could argue quite important x86 design company, where they didn't have the money to go out and really invest in a massive super to kind of solve their complex problems. But instead, I was able to put together desktop machines literally on a folded piece of metal and I would go to Fry's, rest in peace, and purchase
Unfortunately.
off-the-shelf hardware and literally take it back and have one of my guys put it on a folded piece of aluminum and bolt the bits to the folded piece of aluminum, and I'd have bread racks from Sam's Club with like literally 44 machines per rack in an open air data center, because it was designed originally for mainframes. So it was, designed to kind of have an open air concept, and roll in the bread racks of 44 machines, and we could do it and add thousands of cores at a fraction of the price that it would take for us to go to IBM or Supermicro even, or Dell or anybody to have it done. And so, I mean, just the ability to do that, it brings, it allowed that small little 100-person company to compete with the likes of AMD and Intel, and not necessarily effectively compete, as they got bought by Intel last year, but they were able to compete. So, I mean, just that alone, that commoditization of hardware, it's not a bad thing in my opinion. Yeah, it's really cool to work on those really highly specialized systems, but it also it's amazing what bringing that capacity for computing to the general populace can really do.
Well, before I go to Greg for his definition of it, I coming from an enterprise background, I've watched people build commodity infrastructure to solve enterprise problems that probably should have been HPC in the past. And it's interesting to see kind of that merging of the two worlds, where you see HPC becoming more commodity hardware, and maybe those workloads are moving from just general enterprise into an HPC environment where they actually get handled in a much more efficient fashion. So I've been excited to kind of see that merging. But now I'll go to you, Greg. What's your definition of HPC?
Well, before I even mention that, I just want to respond to Patrick's point. I completely agree. We've seen this happen so many times in research organizations, especially government and academia, where in many cases, people, that have never done system administration before are even buying clusters, and, they're not managing them very effectively, but they're getting research done. And because of small budgets, they're actually able to do very good research on that. At some point, typically they'll graduate and be able to then to have proper support for those systems. So it's not a grad student or even an undergrad or a postdoc who lost a bet and now has to go maintain that system. In many cases, then they can actually reach out to somebody like Gary's group at Berkeley and LBL to actually solve that problem and actually manage it appropriately. But it hitting commodity has lowered that barrier of entry so high that it's been fantastic. Now, to get to the question you asked me on Zane, I've been doing this for long enough to have a very strong opinion of what high performance computing is, or rather was. It was tightly coupled, parallel processing at massive scale. And I remember times where, unless you can prove that your application could run effectively at massive scale, you didn't get time. You were actually, you were down revved in terms of how much time you can get and what priority you get to run in, unless you can demonstrate that level of efficiency. Now, we called it the long tail for a long time, which was all of the scientific applications and workloads that are running on these systems that are not that massively traditional high performance computing profile. And what we've seen over time, at least what I've seen over time, is that that long tail has just continued to grow. Grisnog, you kind of alluded to that as well, that the long tail has now grown so far out that the long tail is now becoming the dominant form of workload on many of these systems. And I've had many, many arguments over drinks at supercomputing on what is high performance computing, and is these sorts of applications actually high performance computing. It took me a long time to actually to get to this point in my maturity as a person, to actually say that high performance computing is now more than just those massive tightly coupled applications. it's anything that's going to spin or peg some aspect of that hardware at 100%, and then literally kind of bottleneck based on that subsystem of your hardware. So whether that's CPU, whether that's memory IO, whether that's bandwidth, you're going to peg something on your system. And that's kind of where I am in terms of the definition of high performance computing. It could be a single thread hitting one core, or even a hyper thread on your CPU, but it's pegging something, dang it, somewhere. That's where I draw the line.
I like it. Efficient utilization of resource. That's all I'm hearing.
I'm not sure if it's efficient in many cases, but it's definitely utilization.
Pegging it, resource, whatever. Gary, your definition. You've got a fairly large environment to deal with, so.
It's interesting when Greg talks about that. It brings back a lot of memories. It was exactly the way he said, where we're looking at really big usage of the system. But we do take a kind of a simplistic view of like what is HPC. We work with a lot of researchers, large team science, and then also individual researchers. And a lot of individual researchers may have a very powerful workstation, they may have a laptop. And then at some point, whether they're doing data acquisition or simulation, they're going to outgrow it. And so they have to move to something. And then, so what is that something? And then for us, that's where we define the HPC. We want to move them onto instead of coming up with one-offs or all these people, then that's our opportunity to move them into an HPC infrastructure. And then, I think everybody's kind of covered that, but there's enough convergence in the field so that now when you describe an HPC infrastructure, everybody knows exactly what you're talking about.
So one thing I just want to follow on that Gary said, speaking of memories, we did see a lot of people that started off on a laptop, then went to a powerful workstation. And then when we first started the HPC project at Berkeley, it was around this concept of something called mid-range computing. And mid-range computing was, we defined as everything between a workstation and a giant facility like NERSC, and everything in between. NERSC at that point was limiting people unless they can prove, a reasonable amount of performance and efficiency in terms of running on their system. They didn't want applications running on that system unless they were efficient on that system, because it was such a big, expensive resource. So one of the big motivations that we had for this group was this idea of mid-range. And how do we solve these mid-range problems? And that, to me, is now turned into what I kind of call sweet spot computing. This is where most people are focused on. This is, for example, in high-performance computing, this is the vendor's bread and butter. This is where they're selling the most systems. And that's why we're talking about turnkey HPC, honestly, because it comes right back to that. That's the problem set that we actually really need a solution for.
Yeah, that was a huge gap. I think essentially when we did that early, we helped to define what is known as the mid-range computing segment within the DOE.
And I think that actually even articulates how HPC was changing even then, Gary, without us even really kind of coining it or thinking about the nomenclature. We were changing what was HPC even then. It started off being those giant systems, and then it was moving towards mid-range, and it's been still kind of following in that trend and in that direction ever since.
It's very interesting. Thank you very much, Gary. Next, we'll move to Glenn. You have an interesting perspective on this. So what is your definition of HPC?
So when I started in this field, HPC was, tightly coupled, pretty large scale machines, right? Mirror nets, low latency interconnects. But when the life sciences started adopting the Beowulf architecture, it rarely had those low latency interconnects because it didn't really need it. It just needed, so they were coining it high throughput computing, right, on Ethernet. And so I read into people, oh, it's not really HPC, it's just high throughput. But in my head, I was like, same architecture, just it doesn't have your low latency interconnect. You're like, we're doing and it's a different, type of parallelism. But I still thought that it has to be something like HPC. And then in my head, it kind of evolved to like, how do I, lump those two together? So then that became research computing. So research computing was, all these folks, whether it was molecular dynamics or just, DNA alignment, embarrassingly parallel or tightly coupled. It was all research computing, but then the enterprise was doing it. So, so now what do I call it? And then to John's point, I've worked on machines with, all these GPUs, they're running a Jupyter notebook, but you better have that Rapids library and that Python tuned, optimized really well so they get the most out of it. And so that at my last employer, when we were working on my title, which was not VP of freaking sweet ideas, unfortunately, we talked about, well, why not scientific computing? You're trying to get science done, really, whether it's Johnson & Johnson trying to figure out how to design their next shampoo bottle, or if it's COVID kind of genome analysis. So I've come to call everything that we've just talked about scientific computing. But if you had to like nail me down to HPC, I'd be thinking of systems that try to look like the top 500, right? Tightly coupled, the scale of a top 500. Anything smaller than that is still HPC. I'm not sure my mid-range HPC red line is, but that's how I kind of view the world these days.
Thank you, Glenn. So kind of between what Greg had talked about and what you talked about, I used to be on a mid-range team, and mid-range to us just meant the Solaris team. And one of our one of our
the
guys
engineering
called
workstations.
Himself, yeah, exactly. One of our guys called himself the VP of Blinky Lights because we had the data centers. So
wow, that's a good
not
one.
quite as cool as Sweet Ideas, but pretty cool. Forrest, what is your definition of HPC?
I would define HPC kind of surrounding the efficiency that we're trying to achieve with HPC. We have, hypothetically a single commodity server that we're trying to, do some traditional HPC workload on, whether that be, a simulation or, just to roll them both into one thing, is some type of embarrassingly parallel high throughput type of job. If you only have one server, you're not going to be able to get the performance that you would need out of that in order to actually, efficiently iterate on the work that you're trying to do. So to me, HPC comes down to being able to do these really, really complex things in an efficient way, regardless of what the system underlying it ends up being, whether that's, a bunch of EC2 instances, that's, a traditional tightly coupled cluster, whether that's a cluster that's more meant to provide as many GPUs as possible, just to, do mass model training, that type of thing. I think ultimately it comes down less to the comprisement of the system itself, but are you building the system to gain performance beyond what you would get with, the base component of this system? In that case, I would say you're doing HPC. I would also touch on kind of the long tail concept, because kind of where I very, very first entered this was more so in those tightly coupled jobs. But especially at my last institution, I started to see a lot of researchers coming out of what I felt were non-traditional places for HPC. We weren't just having, genomics people or simulations people, that type of stuff. We also had, education or people from, the education department that were trying to do mass data science crunching for their research. We had people kind of on the high throughput side. We had people that were taking LiDAR data and doing huge amounts of analysis on that kind of in a high throughput way. So I definitely think that in addition to it kind of being about efficiency, we're definitely seeing, kind of enterprise and some of these other use cases realizing that they are trying to do HPC without realizing that they're doing it. So we kind of see, maybe some of the muddying of the waters here as some of these non-traditional entities kind of enter the HPC sphere.
Absolutely. And that kind of leads into one of my next questions, Forrest, and thank you for that, is I think we all alluded to it at some point, but have the HPC workloads changed over the years? And we talk about the infrastructure getting better, the machines getting better. I mean, obviously they're getting far and far more and more dense and being able to be more capable, but have the workloads changed over the years? And I will throw that out to anybody who wants to take it.
100%. Absolutely, the workloads have changed. I mean, you've got some of the traditional workloads that are still, that are still around, and MPI based ones. And we touched on this. I can't remember if it was in one of our dry runs or in the actual meeting last week, but we definitely touched base on the, who's still using MPI. What are your percentages of your workloads of different types and that sort of thing. But it was definitely, eye-opening. I kind of expected it in some ways, but it still was very informative that the mixed workload is really here to stay. Even in very specific industries, the amount of workloads that your singular cluster or clusters are supposed to be able to support is massive. You're supposed to be able to support GPU based AI training versus or ML training versus being able to run ultra fast single threaded performance or highly parallelized jobs. You're supposed to be able to run it all in one, and all of those require different really pain points to overcome in building HPC clusters. But I think we're kind of expected to, as designers and administrators and of those environments, we're supposed to be able to provide for all of those in a kind of one size fits all, and it's difficult to accomplish.
I think to some extent, the commoditization of the compute part of this has made maybe HPC simple to do on the compute side, but where the actual interesting stuff being done now, and probably more so in the future, is on the storage side. Storage is actually becoming the critical thing about everything we do, regardless if it's HPC, high throughput, whatever. I mean, at least for life sciences, there a lot of on-prem clusters and on-prem infrastructure exists today because you just simply can't move the data sets around. Like the compute has to be brought to the storage. So the compute's more or less secondary to just getting all your data in one place where you can work on it.
And not only that, the way the compute is being orchestrated or designed is quite different in the enterprise. Enterprise is dealing, I know of use cases where they are dealing with data pipelines at the rate of multiple tens of gigabytes per second constantly coming. That's the data volume that they're dealing with. And the workflows and applications they're running, they do not have anything MPI. No MPI at all. Nobody in that organization knows anything about MPI. So it's not, MPI is not the only HPC, but the data volumes are a lot higher than many organizations deal with, but these organizations don't have anything MPI.
Lack of MPI in the enterprise pushes me into an old man rant moment about a negative connotation of HPC, in that had in the early days of HPC, I remember back 20 or 30 years ago when I was getting started in this, there was an elitism aspect to HPC. You had to be able to afford a cray to do it. It was a very elite club, and not everybody got to join that club. And that attitude carrying forward over the following 20 years from when supercomputing got started led to us having to deal with things today like Hadoop and Spark and Kubernetes and all this just nonsense, complicated, extra complexity, poor performing, because that's the stuff that came out of the enterprise, when at any point during that, we could have just said, hey, enterprise people, how about you help us write a better MPI and let's do this right, efficiently and simply with a simple scheduler.
I don't think it was that it wasn't offered. I think that it wasn't necessarily accepted in amongst industry, because so many different corporations were trying to capitalize on that market. Or, well, here, let me enter my proprietary standard into this ring. Let's go ahead and they didn't want to do it open source either, generally. They wanted to really make it very tight and hey, well, now that you've entered into our ecosystem, you're stuck. And that's kind of the way that came about, I think, and then of course you had the competition, as you said, where now we've got Kube, and now we've got all of these other competing, not exactly optimal frameworks, to put it lightly, that to do a lot of the same workload that, yeah, you're right, could have been much better implemented in HPC.
So let me ask this, Patrick and John. So from an enterprise perspective, if I'm looking at this, the way that most of those other languages and other tools came out was to be simple and fast. And if I look at MPI, it's probably a little more complicated to program for correctly and to get it as efficient as it should be, right? So was it something that, from an enterprise perspective, people didn't want to take the time to learn how to code correctly for MPI? It was just easier to use some other framework. I'm going to throw out Java.
It was a major barrier to entry. So because of that barrier to entry, whether it be I didn't have the hardware to have that high-speed memory interconnect between the nodes, or I didn't have, I'm a undergrad, I can't afford to get time on a super at the lab. I couldn't, or whatever it was. There's always a barrier to entry. Or if it's Intel MPI, do I have to buy into the entire Intel ecosystem? Do I have to go buy an Intel compiler back in the day? Does that mean that now that I'm running on my AMD chips, is it going to be slower because Intel spiked the compiler? I mean, whatever it is, it depends upon the environment, but there was always a barrier to entry. And then, of course, then you had open MPI. So now we've got competing standards.
So I'm gonna push back a little bit because I think it's very use case specific. So the use cases and the applications that we were solving in high performance computing were very different than what enterprise was really even looking at solving. Now the MapReduce kind of focus there, I do agree that we could have done better in terms of cross-pollinating between Hadoop and then Spark and then HPC, MPI, MPI-IO, and other things. And we're starting to see that also happening in AI, right? This is a few years old now at this point. But things like, how do we do training? How do we optimize training? How do we start parallelizing training? If anybody remembers some of the early training frameworks, it wasn't running MPI. They created something from scratch, almost like MPI didn't exist. And they solved it was a duplication of effort. And to the point, Patrick, I think you made this, it may have been Grisnog, but if we would have come together right at the beginning in a better way, more open way, and I think showed more interest in collaboration, I think we would have seen very different outcomes. But this goes back to, I joke about this, in all of the organizations that I've seen and worked with that have HPC focused people, traditional HPC focused people, there's IT and then there's HPC. Even if HPC is under IT, they don't talk, they don't work together, they don't leverage each other because the technology is both so different, but they're solving such different problems. But there's also just this legacy mindset on both sides. It's not until fairly recently, in my mind, containers was the Pandora's box that really started blurring this. It wasn't really until containers did anyone in HPC even care what the heck was happening in enterprise. We took off our at that point. And on the enterprise side, it wasn't until just recently did they start looking at HPC saying, how do we do training faster? How do we do better analytics? How do we get more insights from our data? And that to me was the crossover point. And now we need to actually all come together and realize we're solving very similar problems, and we need to stop innovating on our own and start actually working together and solving problems together. We need to be a big, happy family again.
Need to be, yes.
We were?
Gary, I think it seemed like you were going to add
What do you
something to
mean?
that.
What do you mean again?
Right?
All right.
I just kind of wanted to riff off that a little bit. of a side jaunt, but back to the topic of how HPC is kind of changing. Something that I really see is the hardware side of HPC changing. It seems like for a long time, we had, Infiniband, CPUs, GPUs, and that was, kind of the basic compromise, or, the basic components of a cluster as far as, the compute part. We start to see now that there's a lot of companies that are starting to invest in creating new solutions around some of these very specific use cases. So, now we see for AI, we're only 10 years off of Alex Krasevsky, I think I pronounced his name right there, training AlexNet on 2 GTX 580s. And now, 10 years later, we already have companies that are trying to replace the GPU for AI training because there's better ways that can be done than just on GPUs. So some way that I really see it changing is on the hardware level. I mean, we've got new ways of training AI, new, much faster interconnects than we've ever had available before, new storage technologies. It seems to me like we're really in kind of a renaissance of HPC hardware. The use of PCIe as a broader interconnect than just to put, accelerators into a cluster and stuff like that. We're really, it seems like kind of in a renaissance as far as HPC hardware goes. And our clusters are really kind of starting to change from just the basic CPU, interconnect, GPU type of thing with FPGAs, specialized chips, what have you.
Forrest, I'm glad you brought that up because that kind of reminded me of a question I had for Gary last time. Is he made the statement that his GCP usage has gone up by 3x over the last few years?
Yeah. Mm-hmm.
What is driving that, and is that something that is more hardware specific, since it is difficult to just go purchase whatever you need because it changes all the time? Is that kind of what you're seeing? Is that what's driving that?
I for a lot of people, they're working with workflows. If somebody's wants to put together or string together an infrastructure with a web server and a database and do some computing and move some data, is pretty easy. The term I like to use is frictionless computing, because they're able to kind of do it themselves and without having to, say, wait for a network drop in a data center and then for somebody to set up the machine and all that. So it's a lot faster. That's it. And then probably the other thing is it's really easy to prototype things. The new tools like AutoML and SageMaker make it really easy for people to get started using machine learning. And so it's interesting. We'll onboard people onto the cloud. We'll kind of like prototype it using AutoML or something like that, and they'll get going. And then sometimes what happens is that they'll find out that it costs a lot of money, and then we'll go back, and now that they see how efficient it is and how this helps their science, we'll go back and transition onto our on-prem HPC using maybe slightly different tools.
Interesting. Yeah, I was just curious because it's interesting to see how that's taking place. And I talked to a lot of different customers who are HPC that are trying to, like you said, try things out in a cloud before they actually make the investment to see if it's going to work for their needs or do what they expect it to do. So thank you. I think we have a question from Mystic Knight. So before we pop it up, I can go ahead and start reading it. Nobody's really talked about the vector processing as a part of HPC build-out. So the example that's given is a medium-scale IoT collection and analysis of billions of devices generate tens of bytes per second, driving anomaly detection, pattern recognition, and other applications. It's an interesting topic. I don't know if you guys have any thoughts on that.
I'd be curious to hear if anybody's ever done anything on a cluster that was in real time. And the closest I've ever got was a group that wanted to produce a weather forecast every day. And so they had data arrive and then they had a deadline to get stuff out. But I don't recall ever having anybody want to do real-time stream processing as part of a cluster workload.
Actually, Krishna and Greg and I could probably have an example of where we're currently building a system for a gamma ray detector, and this the system is going to be the first level trigger of the data coming off the detector, and it's going to be a Kubernetes cluster. We're going to run different containers depending on what's going to be analyzed. But we are using, instead of FPGA hardware, they figured it's going to be a lot more flexible to do it with a cluster. So that's currently being put together, engineered and put together right now.
So to kind of, and I kind of figured, Gary and Krishna would have some examples here, but yeah, there were multiple different examples of people doing detector research, and they basically, you can think of a detector as basically, a very kind of simple idea of one is, you have some sort of reaction happening within a spherical enclosure, and then you've got a whole bunch of detectors all the way around the spherical enclosure. And it's monitoring all of the different types of rays and what is happening at the center of this sphere. And all of these different detectors are creating streams of data. Then these streams of data have to be computed in parallel in real time, so you can see and visualize what's happening within that experiment. And sometimes these are actually in real time, but in many cases, it's near real time, which basically means now you actually have to look at it and then decide, do you want to rerun the experiment? Do you have good data? And then feed that back into your process flow. But it needs to be either real time or near real time for that. And as Gary just mentioned, if you're running it through Kubernetes, it's an extraordinarily different architecture than what we've been doing in high performance computing. And without even knowing the specifics on that, I would say probably it's a bunch of services that are running and doing the equivalent of like an inference on each one of those data streams coming in, and then computing on those via GPU. So this is like a performance critical service that's running. And Kubernetes is a good architecture for managing services. I'd actually, I'm curious on the efficiency that you're getting, because I've actually had really bad results with regards to Kubernetes. And just to go on a quick tangent real quick, we actually were talking to some people that were doing something along these lines with Kubernetes, but because Kubernetes is so big and bloated, it was usually utilizing about 15 to 30% of the underlying hardware resources just to run Kubernetes. So now let's scale this up. Imagine buying a 5,000 node cluster or even a 500 node cluster, and 100 nodes out of your 500 nodes is just running your scheduling system, your orchestration system, right? And you're basically losing 20% of your system to run just for Kubernetes. So at a small scale, I think Kubernetes would do it, but as soon as we start scaling bigger, we've got to come up with better ways of doing that.
Yeah, another approach I have seen in the industry for these real-time stream computers is a traditional way, which is, so if you look at a DDN appliance, a storage appliance, they usually come in pairs, and they come with some fault-tolerant, resilient designs using basic technologies like HA proxy, CoroSync, such that services can flip from one controller to the other controller automatically if there is a failure in top controller. So cluster services can move on to the bottom controller. That's the basic components that anybody would use for fault tolerance. I'm sure even Kubernetes is kind of built on some base components like that. In the industry, I have noticed if you build a real-time stream computer where your machine goes into a production pipeline and they need real-time feedback of the quality of the product being manufactured, and if this computer is down and that quality is not being generated, depending upon the value of the product you are making, it can cost multiple $100,000s of dollars per day of production loss. So that's very costly. So this real-time computer giving the feedback on the quality of the product is a very critical component. And when you're making designing such a computer, fault-tolerant designs, having backup components so critical, and things falling back automatically from one server to other server is such a critical thing in your design. If you do not have it, you are costing hundreds of cases of losses to your company, to your product. That is something that I'm noticing heavily, and not everybody in the enterprise is adopting Kubernetes. They are just trying to accomplish that using the HA proxy co-hosting services, which have existed for a long time, and trying to put together everything. Like we have redundant switches, redundant network cables run from servers to switches, and have services for failover from one switch to the other switch if there is a switch failure or network cable failure. Um, those are another tangent and extension to HPC design that I am seeing in the enterprise, and that is very critical and needed when you are making building a real-time computer for these use cases.
So from my past IoT experience, most of what we were trying to do was do as much analyzing of data at the edge as we could, so that we weren't sending massive amounts of data back to be processed or analyzed. You were looking for that anomaly, and then whatever data was driving that is what we were sending back. So from a real-time usage, I feel like just because we were trying not to send a lot of data that may have been irrelevant, we were doing a lot of pre-processing at the edge and then only moving back what was necessary for the next type of action or the next type of event that needed to be taking place. But it's an interesting question when you're talking about massive data, like in Greg's example. It's not really an edge use case because everything is right there together. You're trying to do it in the place that it's taking place. From an IoT perspective, when you have billions of sensors out, that amount of data streaming back could be something that would be overwhelming. And a lot of that at the end of the day just gets dropped on the floor and you never even look at it. So a lot of different ways to approach it when you look at IoT. It kind of depends on what you're trying to accomplish, in my opinion.
My history with this was back at Bell Labs. We were monitoring numbers of phone switches in real time, and in order to do that, it required. I mean, this was quite a long time ago. This was the era of the 5E, which that should kind of explain how old this was. But and they were quite new. It was one of the first digital phone switches, but it was required massive amounts of customized hardware to monitor these switches. And today, I don't see the investment in that type of customized hardware for real-time computing as much. I mean, it's kind of common, or I'm sorry, kind of uncommon to see, really, really specifically focused hardware for real-time computing like we used to see quite a lot. I mean, you'd see, real-time Linuxes, you'd see real-time, that were made for all sorts of different RTC clocks and RTC controller cards and things like that to ensure, absolute, peak timing and synchronization. And we see some of that today, but not nearly that we did maybe 20 years ago. So I think there's either because the performance of machines has gotten so much better and we're close to a okay level, or our standards have slipped a little bit. I think, or maybe maybe a merger of both. I'm not sure, but
yeah, that's great. Thanks, Patrick. So we do have a question from Sylvie, and it's: have the programming languages and interfaces changed over time?
I think it's a great question. There's yes. When I was first getting into this, Gary, you may attest to this. We actually had to help a lot of scientists and researchers upgrade to Fortran 77, upgrade to Fortran 77, because they were running predecessors. I forget what Fortran was before 77, 60 something. And that was the year, by the way, that the spec was created. And yes, it has definitely changed. And we've seen a lot of that. Now on parallelization, we've seen MPI really taking off. We've talked a little bit about the different forms of MPI, but the specification has definitely evolved over time. But that specification has created a lot of compatibility. So even though we have many different MPIs, coding for any of those MPIs should be the same no matter what, right? If you're adhering to the strict specification, There's some alternative or optional pieces of the specification, but as long as you adhere to the strict specification, it should be MPI compatible no matter what. Now, every programming language is going to have its own aspect of or interface to MPI. So you could have, for example, C bindings, Fortran bindings, Fortran 90 bindings. And more recently, we've seen a lot of interest in higher level programming language like Python. And Python has absolutely taken off in scientific computing to the point where I actually think it's probably one of the most dominant programming languages nowadays. And I'm kind of curious from others, are you seeing the same thing? And what is that like in industry specific areas like life sciences? Is it similar there too?
Our software stack is almost entirely Conda at this point. Like there are a few applications in there, Bowtie, SAMtools, that kind of stuff that is not in Python, but for the most part, got to be at least 70 or 80% of everything is done in Python. Maybe with a mix of R in that too.
Glenn, are you seeing the same thing in your area of life sciences?
Yeah, things have evolved from Perl to Python. Python has really done a fantastic job in adding libraries, and then of course Conda to support the researchers. It's, I think, the most popular language. There is a lot of R in there from folks who come from a statistical side. They seem to like R a lot, but Python is and this is just my opinion, but if you're trying to do a lot of other things than just statistics, Python is much better. You're not bringing up a web server in R. So we see Python doing a lot in the life sciences. The folks that are using C are the folks in writing the algorithms, whether it's for DNA alignment or drug docking or on the GPUs, trying to get their stuff onto the GPUs with CUDA. Those are the folks using the low level languages. Everybody else is a little bit higher up at the Python level. There seems to be a little bit of a push to, I can't remember the name of the project, but actually getting some actual typing as opposed to just static typing, as opposed to just dynamic typing with Python for some things in research. So I'm actually kind of interested to follow that. But yeah, that's what the trend has been.
It's funny for me even to consider and think that HPC has changed so much over the years that we're not even focused solely on compiled and purely efficient languages, that we're running across a whole bunch of different languages. I think there's even some Rust that I've heard of. Patrick, I think you've mentioned Rust as well, kind of coming into HPC.
There's Rust, and also, I mean, there's still some Ruby creeping around in the EDA world, and moving in there. And let's see, but primarily these days it's Python and Rust, and again some Ruby, and of course, sadly, that Perl still exists. The Swiss Army
hurts. That hurts.
You're making Greg cry.
That hurts.
Sorry.
We're talking compiled
sorry.
Perl. That's why he was leading to Perl. Compiled
Okay,
Perl.
are we done with the webinar yet? Come on.
No, I love the Swiss Army chainsaw, but I also hate it. If you've ever walked into a project where you've had, somebody they've been in their own Perl world for years and years and years, just designing it and just adding on, and then you try to take over that project and figure out what was actually done with this stack of Perl scripts. It can be fun.
And then you rewrite it in Bash in like 10 lines.
And make you hate Perl.
Yeah. Yes. Dave, so we have a new question from Dave. I've seen so much scripty and numpy usage at scale these days. There are a lot of compile time optimizations to be considered for those libraries alone. Intel compiler MKL.
SciPy, by the way.
What did I say? Sorry.
Skippy.
No, sorry.
Because I heard Skippy. Maybe I heard it wrong. I
I don't know.
don't miss any opportunity to poke at you, Zane, and because
course
there's
you
not
don't.
many. There's
I
not
would be
many.
disappointed if you didn't know. Whatever.
I just read it as spicy.
Now I missed it.
Okay.
Do you have a question, or is this just like to make fun of Zane time? I'm good with that either way.
Well, as I said, it doesn't
I'll give you
happen
plenty of
often.
reasons. Whatever.
Doesn't happen
Plenty of
often,
times.
so I have to take every advantage that I can.
Well, ask Matt. It happens all the time because he's good at it too.
I got my shirt on.
Exactly. Well, look down.
Yeah, yeah.
great.
So, yeah, there's a lot of scientific libraries that are also becoming more and more available for Python and other higher level programming languages like SciPy, NumPy, and others. I haven't seen, and I'm curious if others have seen, architecture optimized math libraries like MKL, like Intel MKL and whatnot. Are there interfaces for Python for these, or are we kind of moving away for the kind of specific need of high performance and absolute tuning and profiling and building the fastest programs ever in exchange for kind of more general purpose HPC applications and whatnot? I'm kind of curious. I know we're kind of at the top, and I'm really curious on people's take on that. And maybe that's where we leave off for our next roundtable.
It's got to be at least 7 or 8 years since I built a BLAS library to do specific optimizations. I think at some point the hardware got fast enough that people, certainly at the level that I have to deal with, they don't care about getting the last 5 or 10% out of anything. Right? Like the next generation of processor will solve that problem for us. They focus more on the writing a better algorithm in general rather than trying to get a little bit more compiler optimization out of it.
When Intel came out with their like Intel Python and then like MKL and BLAS and Boost and things like that optimized underneath, we were really excited to use it, but it just didn't seem to play well with the typical like Conda pip tools. So when we try to install it, like it just kept blowing up on us, and so we gave up on it because we thought we could get a lot of good performance gains of it because everyone was using Python, but just it came down to just usability with or just trying to introduce it into already kind of a mature Python environment that everyone was familiar with. Hey, just try to use these libraries and things like that. It just kind of it didn't work, so we eventually dropped that. But yeah, other than that we haven't built or compiled anything specific with for tuning or a library in a really long time.
Yeah, I think my most frequently used C flag is mtune generic. Just because I want it to run everywhere, right? I don't care if it's fast. I just want it to work everywhere I'm going to run it.
That's where it really comes down, is that you can make snowflakes that work really, really, really well one time. Making something resilient that can run everywhere all the time and reduce your issues is so important to HPC, in my opinion, because if you're constantly retuning for different architectures and different like that last 2% of optimization, then how much time are you losing to get that 2% when you could just throw more hardware at it, throw more cores, throw more memory, or throw a cloud at it. I mean, that's the other aspect, is now that you can fairly easily scale up, it's kind of like for some of that, it's easier to do that than it is to optimize like just down to that little tiny little bit at the end.
Thank you for that, Patrick. We have one more question before we wrap up. Are there analogs to MKL for things like the ARM 64 architecture?
So I don't have an answer specifically for the question. I would assume if there's not already that they're going to be coming, they're coming soon. But I just wanted to say, hey to Dave, it's been a long time since we chatted. It's great to see you here.
And thanks for all the questions, Dave.
Does anybody else know if there are optimized versions of math libraries for ARM? Dave, we're going to probably have to reach out to some people that are running some ARM clusters. I know Sandia has some pretty good size ARM clusters, and as well as maybe some ARM people, and we will hopefully have an answer for that either in the chat or maybe for our next webinar.
I'm taking notes. Well, guys, we are a little bit over, and we do appreciate your time. We know you guys are busy, and thank you for joining us again. Krishna, it's nice to meet you. Gary, John, Patrick, Glenn, Forrest, as always. Greg, thank you very much. Guys, go out, like, subscribe, and we will see you next week. Thank you very much.